Hello everyone, I am Dr. P.S.V.Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the MOSFET. MOSFET, Metal Oxide Semiconductor Field Effect Transistor. So at the end of this lecture, the student will able to understand the construction of MOSFET. He can also understand the VI characteristics of MOSFET. Now coming to the metal oxide semiconductor field effect transistor, that is MOSFET. So this is the circuit symbol for the N channel MOSFET. There are actually two modes of N channel MOSFETs. One is N channel depletion mode of MOSFET, and the second one N channel enhanced mode of the MOSFET. And I am taking here N channel MOSFET. There are actually three main parts of this one. One is the source, drain and gate. Source, drain and gate, these are the three main parts of a MOSFET. And coming to the construction of N channel MOSFET. So in this N channel, this is the circuit symbol for the N channel MOSFET. In this one, a lightly doped p-type substrate is taken. This is a p-type substrate taken. It is the base of the material, or p-type substrate is taken, into which two heavily doped n-type regions are diffused. So this is n-type region, or n plus, means heavily doped n-type regions are diffused, which act as drain and the source. So the first one is acting like the source and the second one is acting like the drain. So these are heavily doped n-type semiconductors. They are diffused into the p-type substrate of the device. Now these n plus regions, they occur the diffuse to form N channel connecting the drain and the source. Actually in between these two, N plus and N plus, they are acting as the connectors, means from source to drain some current flows because of this heavily doped n-type semiconductors. And a thin layer, later on a thin layer of silicon dioxide is grown over the entire surface, and the holes are made to draw ohmic contacts for the drain and source terminals. When you observe, this is the silicon dioxide layer. So this is an insulator layer. On that one, two holes are made through which we are providing the ohmic contacts there to connect to source and the drain. So two ohmic contacts, two holes are drilled there and ohmic contacts are provided there, so that we can have the connections. Leads we are providing from source to means source and drain, two connections we are providing there. Okay, and afterwards a conducting layer of aluminum is laid over the entire channel upon this silicon dioxide layer. You observe on the silicon dioxide layer, one aluminum layer is provided. It is provided to provide the gate. This is acting like the gate. Okay. Actually, you observe this kind of construction, the base is taken as the p-type substrate. It is a p-type substrate. On that one, we are diffusing, we are providing two n plus regions, heavily doped n plus regions are provided. Automatically they are acting as, one is acting like source, second one is acting like the drain. On that one again we are providing the silicon dioxide insulating layer, and on that one we are providing the gate material. To get the gate, we are providing, say, aluminum one layer is created there, that is acting like the gate, whereas on the silicon dioxide two holes are drilled, and through that one we are providing, say, the two leads ohmic contacts, so that acting as the source and the drain things. And because of this construction, you observe this construction, the area occupied by this n channel MOSFET, it is only 5%, it is occupying only 5% as that of the BJT. That's why in a chip so many this kind of MOSFETs we can construct. So that the IC area will be reduced drastically. That is the advantage of going for these MOSFETs. So when you observe this one, only 5% of the BJT bipolar junction transistor area, it is just occupying because of this kind of construction. This is the construction of n channel MOSFET. And whereas coming to the working of n channel MOSFET, actually two types of n channel MOSFETs we are discussing. One is the enhanced mode and the second one is called, say, the depletion mode. In case of enhanced mode, what is meant by the enhanced mode? Actually, for this kind of one, we are keeping the gate at the positive voltage, means VGG. I am giving VGG at positive voltage, and the source to, that means this is VGS, gates to source, it is connected under forward bias. So you observe the negative terminal is connected to n plus channel, means source, and this VGG positive is connected to gate. When the gate is connected under forward positive voltage, when the positive voltage is given, what happens? So actually in the n plus region, source as well as drain, of course in this region electrons, say, they are attracted towards the gate. They are attracted towards the gate, and this gate repels the minorities, actually the holes. Therefore electrons are attracted and the channel is created here. Now the electrons, you observe the drain. So whenever there is no biasing voltage at any case, only the gate is not at all given. Suppose if the gate is not given any voltage, so what happens? From n, means source to gate, current is flowing, so it creates some kind of current, drain current. And when the gate is connected or it is given a positive voltage, what happens? More number of electrons, they are attracted towards this one and automatically they will diffuse. Here the drain, say, observe VDS, drain and the source, this is connected under reverse bias always. So under reverse bias, automatically these electrons are dragged towards the drain, or they are attracted towards the drain. More current flows at this case. So when you observe the forward voltage, we are giving the gate voltage starting from 0. At 0, little bit current is flowing from source to drain. When you give only 1 volt for the region, again more current is flowing. In this one ID, drain current becomes more. When you give 2 volts, again it increases. Again you give 3 volts, again it goes to high. This is actually called enhanced mode. So the current is enhanced in this one, hence it is known as the enhanced mode of operation. So coming to the next one, depletion mode. So in the depletion mode, when you observe this the circuit diagram, here VGS, voltage between the gate and the source, you observe the gate is kept at the negative voltage. Again as usual, when there is no voltage given to the gate, what happens? From source to the drain, a little bit current flows, because more number of negative charges are there, automatically the electrons will diffuse. When this is connected at the reverse voltage, what is that? VDS is connected at the reverse voltage, means say the positive terminal is connected to this drain, the electrons are attracted or they are dragged towards this one. There exists some drain current, some little bit drain current flows. But when the gate is given the negative voltage, what happens? VGS, means gate source, this volt potential difference, negative terminal is connected to gate and the positive terminal is connected to the source, say what happens in this one? Automatically gate is kept at the negative voltage. Because of the negative voltage, the holes are attracted towards this one. You observe the positives, they are attracted towards the gate, whereas the majority carries electrons, they are not attracted, they are repelled. As a result, what happens? Initially the current is flowing between the source and the gate, now it is a little bit reduced. So this is depleted somewhat. That's why as we are increasing the gate reverse voltage, automatically the current is reduced a little bit. That's why it is called depletion mode. When you observe the depletion mode of operation, at 0, as usual, there is some gate current, ID means drain current. Gate voltage is 0, no biasing, no voltage is given to gate. Automatically ID, the current, it is showing at the central line, so some current it is showing. When you give -1 volt, means in the reverse case, gate voltage is 1 volt, 2 volts, 3 volts, negative voltage we are giving. As we are increasing the negative voltage, so the drain current gradually decreases. That's why it is called depletion mode of operation. So these are the VI characteristics of the MOSFET. Moreover, N channel MOSFET, so two operations, one is enhanced mode and the second one is the depletion mode. When you observe the transfer characteristics define the change in the value of the VDS, voltage between, so the drain and the source VDS, with the change in the ID, that is ID current, the drain current, and VGS, voltage between the gate and the source in both depletion and enhanced modes. Actually this graph represents the ID, means the drain current under two kinds of operations, depletion mode and the enhanced mode. Already we have seen under depletion mode we apply the drain voltage, that is negative voltages. Under enhanced mode we apply the gate voltage negative, whereas in case of enhanced mode, the gate voltage we are giving the positive voltages. So under the enhanced mode, as we are increasing the VDS voltage, automatically so the current ID current is increasing, and whereas in case of the depletion mode, as we are increasing the VS negative voltage, so it is decreasing. This graph represents the transfer characteristics of the enhanced and depletion modes of N MOSFET. So coming to this one once again, MOS, metal oxide semiconductor field effect transistor. It is a metal oxide semiconductor field effect transistor. So it is this is the circuit symbol for this one. Enhance N channel MOSFET I am taking. It is operated under two modes. One is the enhanced mode, another one is called the depletion mode. So coming to the general construction of this one, P-type substrate is taken. On that one, N regions are N plus heavily doped N regions are diffused into that region. Automatically they are acting as source and the drain. And to get the ohmic contacts, okay, first initially a silicon dioxide layer, means an insulating layer is kept on that one, insulating layer is kept, and on that one two holes are drilled automatically to get the ohmic contacts there, to get the source connection and also drain connection. And again on this silicon dioxide layer, so aluminum layer is taken, it is acting like the gate there. So three parts are there now, gate, source and the drain. Now coming to the circuit connections, we can operate this one under two modes. One is the enhanced mode, another one is the depletion mode. In case of enhanced mode, gate is kept at the positive voltage. In case of depletion mode, gate is kept at the negative voltage. We have to say negative voltage. So coming to the first enhanced mode of operation, suppose in both the cases when there is no voltage given to the gate and VDS is applied, say automatically from source to drain little bit current flows, and some because of the diffusion of the carrier some current is flowing there. Automatically we can observe some current in the VI characteristics at G is equal to 0. Now coming to the enhanced mode, positive voltage is given to the gate. What happens? Under positive voltage, the electrons here, they are attracted towards the gate, and the holes, minority carriers are there, they are repelled there, and of course they are attracted. Automatically a channel is created there. When you supply VDS voltage, automatically these electrons are they are received by the drain. That's why drain current increases. By increasing the gate voltage, go on increasing the gate voltage, the drain current gradually increases under this kind of increasing the gate voltage. So this is the enhanced mode of operation. And coming to depletion mode, in case of depletion mode, again so the gate is held at the negative voltage, and because of negative voltage the holes are attracted towards that one, electrons are repelled still. So that means this is acting like the depleted case. And when you increase the reverse, means what is the gate negative voltage, automatically initially at 0 gate voltage some current is there, automatically that decreases, and as go on increasing the negative voltage, automatically we get these kind of characteristics. This is the graph representing the ID versus VDS. These are the drain characteristics under VDS voltage. And coming to the transfer characteristics, as VDS and VGS values are taken on the x-axis and the drain current is taken on the y-axis, the depletion mode case, automatically we apply the VGS at the negative voltage and VDS always at the positive voltage, we get this kind of transfer characteristics. So coming to the summary of this one, so in this one we have seen the construction of the MOSFET, metal oxide semiconductor field effect transistor, how it is constructed, how it is reduced the size when compared to the BJT, bipolar junction transistor we have seen. Later we have seen the VI characteristics of the MOSFET, how the drain current changes with the change in the input voltage, all those things, how the VI characteristics are there, that also we have seen in this one. Okay, thank you.